Greetings and welcome, friends. Today we're going to talk about solving equations graphically, which is kind of weird. All right, if you look at this equation I have on the screen, notice it has no y's. It's just a single variable equation, and we technically know how to solve this, right? We would bring our x's together. We would then move things away from the x, and we'd eventually get it all by itself. And I'm actually going to show you a different way to do this, and it's not tremendously more helpful with the current types of equations we can solve, but throughout your mathematical careers, you'll actually be able to use this new method to solve, maybe even at the end of this video, I'll show you how we could solve a type of problem that we wouldn't be able to algebraically, but graphically with technology we could. So let's see. So if I wanted to solve this algebraically, like I said, we'd need to bring these x's together. Maybe you guys would remember how to kill the fractions, but let's pretend for a minute that we don't. I'll subtract 1/3 x from both sides, which actually is going to work out just fine here. So let's see. I can so these cancel each other out like I designed, and we're getting the x's together. Negative 2/3 x's minus 1/3 x is negative 3/3 x. What's 3 divided by 3? 1, yeah. So I'm going to just write that as negative x, or negative 1x, minus 1 equals, those got eliminated, negative 4. How could I solve this now? How do I get x by itself? It's being multiplied by negative 1 and subtracted by 1. You could divide. Normally we added just because that always avoided fractions, but in this case dividing actually wouldn't have made fractions anyway, so we'd still be safe. So negative x, these ones cancel out. Negative 4 plus 1 is negative 3. And if the opposite of x is negative 3, then that means positive x is equal to positive 3, right? Yeah, it's just the opposite. So I get a solution of x equals 3. So, right, well, this is the way that we would have solved it before. And I guess that's part of the challenge with showing you this new strategy now instead of like in Algebra 2 is that it won't make itself seem incredibly useful just yet. But let's see. Solving linear equations by graphing. So check this out. To solve an equation when you only have x's here, what we're going to do is write it as two separate linear equations. I'm actually going to take the left side and say y equals that, and the right side and say y equals that. I will then graph both of them and solve. However, I'll only be interested in the x value of the solution. A little bit weird, right? A little bit weird there. It's a little strange there. I think you might agree. So let's actually do this for this last problem, and then we'll continue with the book's regular examples. So I'm going to need a graph. You guys aren't even writing this down yet. That's fine because I didn't give you this problem to write down. But let's see what graphically this would look like. So they're saying the following. Instead of solving algebraically, let's take this piece here and write that as y equals negative 2/3 x minus 1. And let's take this piece here and say y equals 1/3 x minus 4. That I'm actually setting, I'm kind of like unsubstitutioning here, right? I have these two things equal, and then I say, hey, what if I just say each of them themselves is equal to a completely new variable, y? And now let's graph these, okay? So to graph these, what's the slope of this blue equation? Negative 2/3. What's the slope of that blue equation? Negative 1. So I'll start at negative 1. I'll move by my slope. Well, it's negative, so it's going to be down 2 over 3. Down 2 over 3. And I could repeat down 2 over 3, right? And let's draw that a beautiful blue line for us. And I line up my points that are furthest away for a most accurate line. Drawing the line all the time, it's amazing. That was my song about drawing lines. Let's have this next one. Someone tell me, what is the slope of purple here? 1/3. And a y-intercept? B equals -4. So here's that y-intercept. Okay. Let's move by the slope, which is 1/3. So I'm going to go up 1 over 3. That actually lands right there. Up 1 and over 3. And up 1 and over 3. Because our slope is rise over run, correct? You guys agree? Yep, classic. You guys are expert graphers now. We love graphing. Oh, yeah. All right, and then I draw this line. And you guys probably already could have answered it before I drew it. Where do these lines intersect? Right here, right? And what are the coordinates of that point? So over 3, I do the x first, so over 3, down 3. And what this said was that the solution is the x value, okay? The x value. So my solution is this. Is that. Okay? So this is kind of weird. In this case, I would say this was actually more work for us than having just solved it this way. But it does work. I say, hey, let's take the left side, write an equation. Right side, write an equation. Graph those equations, and whatever the x is equal to, where they intersect, right, x equals 3, you could even imagine it was right there. That's going to be the solution. Because I actually didn't care what y was equal to, remember, because I just made up y. There was not even a y in the original problem. All right, so this is the process. Little weird. All right, so to solve an equation, you could set each side equal to y and graph. So that's the weird part. Let's do example 1 together here. We'll do examples together. So now you guys got this. I've got also a stumpy looking coordinate plane, but that's okay. So let's do this together. All right. So they say I've got to break this into 2 equations. What's my first equation going to be? Y equals -x plus 1. What's my second equation? Someone help me out with that one. Well, it'll still be y equals 2x minus 5. And imagine if we were doing substitution. Imagine this was the problem I gave you last week, right? You could have said, oh, Mr. Waddy, check this out. Because this is equal to y, I could have plugged this in right here, right? And that would have given me -x plus 1 equals 2x minus 5. The same thing that I had here. So what I'm kind of doing is I'm reverse substituting. I'm actually making the problem more complicated than it was originally, which is a little bit weird. But that can be helpful for future problems, okay? For future problems, it's going to help us out. So let's see, what's the slope of the blue line? Negative, just the coefficient, -1. What's the slope of the purple line? Just the 2. What's the y-intercept of the blue line? Yep, and y-intercept of the purple? Yeah. Let's actually have you guys graph this, because I already showed you one kind of like it. Let's have you graph it and find the intersection. I'll be around to help. And then I'll show us in a moment. Yep, and then we'll find the intersection. So let's see, for the first line, y-intercept is at 1. The slope is -1, so I'd go down 1, over 1, right, down 1, over 1, etc. You don't have to draw those arrows every time. We're in the habit of it. Hopefully you guys are getting better at graphing these days, though. And our solution, we are only going to be interested in the x-coordinate of your intersection. So yeah. So let's see. So there's my first line. The next line had a y-intercept at -5 and a slope of 2. So going up, and there we go. Up 2, over 1, up 2, over 1. I think I might disagree with your solution, though. I don't know. I'm sorry. It's okay to disagree. Find out. So I draw that line. That's a beautiful line right there. Yep, I like that straight edge tool. So my intersection is right here. That's the point over 2 down 1, or 2 comma -1. My solution is x equals 2. Right? I'm only interested in the x-coordinate of their intersection. They said to check it. Let's do a check. Why not? We haven't done a check in a while. Is the opposite of 2 plus 1 equal to 2 times 2 minus 5? If I plug this into the original equation, -2 plus 1 equals 4 minus 5. That's -1 equals -1. That's true. So that means it checks out. That means it's true. So yeah, we did find the solution. This is, like I said, this is a little bit weird. This problem actually would have been so fast to solve algebraically, but they're trying to like get you into this concept of solving this way. Here, how about, here's a more interesting problem. Let's pick it up a notch. Yeah. Here's an interesting problem. What? Absolute values? No way! Okay, here we go. You guys, I don't even know if you remember this. Do you remember this? Yeah, abs-val. Oh, they gave us a sneaky one. Man. Ah, well. All right, so I'm going to break this up into 2 cases here, okay? 2 cases. Man, they even did this. Yikes. Oh, wow, they actually broke it up into 4 cases? Wow. Wow. This problem's interesting here. Huh. I'm trying to think of which way. Man. Yeah, let's do the 4 cases, I guess. So, guys, for this. Oh, dear. Oh, dear, dear, dear. For this, there's 2 possible situations. One, I can drop the absolute value, and these equations were equal to each other, like so. And this might be more complicated. Oh, well, Mr. Waddy, we'll live with it. Or case number 2, x plus 1 is the opposite. You guys remember the old absolute value, break it up sort of situation? It was either equal or it was equal to the opposite of the right-hand side. It's a little bit weird. I know it's been a while. But that's the situation we've got. We've got kind of these 2 cases. Let's simplify this one. That means this is equal to -2x plus 4. All right. And x plus 1. And so let's actually write some equations for this. My first equation is going to be y equals x plus 1. My second equation is going to be y equals 2x minus 4. I could call my third equation, I'm running out of colors here, this guy, except I don't even need that one because I already have it. So I'm going to say my third equation is this. Y equals negative 2x plus 4. And I'm going to be looking for the intersections of this blue graph, because that was the one that duplicated, right? I'll do it here and here. Of this blue graph with the purple graph and the blue graph with the green graph. So let's try to graph these. So for the blue graph, x plus 1, the y-intercept is at 1, and the slope is positive 1. So I'm going to go up 1 over 1, right, up 1 over 1, up 1 over 1, up 1 over 1, and draw a line. I actually want to show you this the absolute value way later. Okay, so here we go. Like that. There's the blue graph. Now the purple graph, y-intercept is at negative 4, right? With a slope of 2. So that means up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I think I found my first intersection here. And let's graph the green graph. What's the y-intercept for the green graph? B, the y-intercept. Yep, so I'll start up at 4. And what was the slope for the green graph? The slope is the negative 2. So I'm going to go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. We'll draw that. Why is what? Because they had a different slope? I don't know. Yeah, this one has a negative slope. The other two have positive slopes. Okay, so my first solution occurs at the intersection between the blue and purple. Blue and purple is right here. That intersection is at over 5 up 6. So my first solution is x equals 5 is the thing that makes this equation true. All right, I only care about the x-intercept here, because y didn't even originally exist in the problem. We introduced y. My second solution is the intersection between blue and green. Where's blue and green intersect? I don't care about this one. This one that I care about, right? What are the coordinates there? Almost 1, 2. Over 1, up 2. For x and y, for ordered pairs, we actually do left, right before we do up, down, unlike slope, which is always rise over run. So there's 1, 2. So that means the solution of this equation is x equals 1. Like that. Because I only care about the x value there, right? And so that means this original problem has 2 solutions. Yeah. And then I can even check our solutions in the original problem if we want. Let's we'll do a check. I think it might be worth doing a check this time. So for a check, this problem's a little bit crazy here. A lot of moving parts on this. All right, so let's check 5. Is the absolute value of 5 plus 1 equal to the absolute value of 2 times 5 minus 4? So that's abs 6. Is that equal to abs 10 minus 4? That's abs 6 equals abs 6. What does absolute value even mean? Or what does it do? Absolute value is the distance a number is from 0. 6 is 6 units from 0. So for positive numbers, it leaves it. For negative numbers, absolute value makes it positive, right? Remember that? Let's check 1 in the equation. So the first one worked, 5 worked. Let's check 1. So is the absolute value of 1 plus 1 equal to the absolute value of 2 times 1 minus 4? This one actually is going to utilize the absolute value part. So abs 1 plus 1 is abs 2. 2 times 1 is 2. That's abs 2 equals abs 2 minus 4 is negative 2. Absolute value of 2, how far is 2 from 0? It's 2 units from 0. How far is negative 2 from 0? 2 units from 0. That means both of those work. That means both of our solutions are true. Cha-ching. Cha-ching. We found 2 solutions. Now what I want to show you, and this is where, let's say, because, I mean, up until this point, I think maybe we saw one double absolute value equation before. It's a little bit tricky. Let me pull Desmos up here. Wonder if I can. No, that's not helpful. Oh dear. Oh dear, friends. What did I done? Let me maximize again. Okay, there we go. So I'm going to write these as 2 equations. Let's write y equals abs x plus 1. I don't know if you guys remember graphing absolute value. Remember it was the V graph? Looks like that. Can I have like more than just 2 eyes on this right now? Anybody? No? All right, so there's the first graph. Let's graph this one over here, 2x minus 4. Y equals abs 2x minus 4. Ah, I did 3. Good call. 4. There we go. So here are 2 different absolute value graphs, right? The solutions to this equation, which had no y's in them to begin with, I introduced the y's, occur here, here. What are my solutions? The x coordinates of those points. So at 5 and at 1. At 5 and at 1. Are 5 and 1 my solutions? 5 and 1 were my solutions. Craziness, huh? Craziness. All right, tricky tricks. Tricky tricks. All right, let's see. I think there's one more that I want to show you. And this is one that I made up just moments ago. Here we go. You ready? Let's solve, because this is one that, so this is just example question mark. 3, I don't know. I'll call this 2.5. How about 2.5? I like it. Solve the following. All right, you don't have this on your paper, so just follow along. X squared minus 4 equals 2x minus 4. You don't know how to graph that yet. Maybe by the end of this course, I hope we'll get there. But using this strategy and technology, it's doable. What we would do is we'd write an equation, y equals x squared minus 4. That's x squared. X to the second power, yep. We'll talk about exponents soon, don't you fret. And I'd write a different equation, y equals 2x minus 4. We know how to graph this one. This one's a line. We don't know what the graph of that one looks like. But let's open up Desmos and graph these. If I can find the intersection between these, this is telling me that the solution of this yellow equation will be the x coordinates of the intersection. Or intersections, which there's going to be 2. I kind of gave it away. So y equals x squared minus 4. Let's do that one. So x squared minus 4. I got like a, what do you want to call that red shape there? It's like a U shape. It's called a parabola. We'll talk about those later. Yeah. And then the other one is 2x minus 4. So guys, so if I look at this, where are my intersections? One is at 2. But my solutions, yoink, took a screenshot there. my solutions are going to be the x coordinates of these. What are my x coordinates? One of them is 2, so I get x equals 2, and the other one is at 0, so I get x equals 0. So I actually can now solve an equation that I don't know how to solve yet, or you guys don't know how to solve quadratic equations yet. But if I was able to graph these, I actually could use this little graphing trick to help myself out. So even me, as someone who's got a math degree and all this, if I'm solving a problem and suddenly it's got like crazy stuff that I'm not used to solving, I could write it as 2 separate equations, graph them, and find their intersections, and then those intersections will be my solutions. Let's do one check just for fun. We're here, right? Yeah. Let's do one check, because I want you guys to believe this. Is 2 squared minus 4 equal to 2 times 2 minus 4? 2 squared is 4. 4 minus 4. 2 times 2 is 4. Uh-oh, this done looks true. 0 equals 0, that's a true story. Not infinite. This one had 2 solutions. This was a check. When I do a check, I'm supposed to end up with a true statement. When I'm solving, and my variables all disappear, that's when you might have an infinitely many solution. During your solve, if your variables disappear. If I'm doing a check, there were no variables to begin with, so it was already going to come to a true or false. All right, well, thank you for watching, mis amigos. Adios.